Chloride are next.
Ammonia and ammonium chloride?
Yeah.
Okay. I haven't talked about that yet, aqueous ammonia. We didn't do any aqueous ammonia in the lab. So just focus on the ones we did in the lab. I'll talk about aqueous ammonia when we get to the acid-base chapter right now. So skip all those.
Skip all those.
Yeah.
All right.
Aqueous ammonia you're not going to have on the test. So you don't have to worry about it. Okay, other questions? Anyway, that one has no driving force.
It has no driving force. Okay. I also wanted to understand why they have an H2O as a reactant.
For which reaction?
For the aqueous ammonia and aluminum chloride, they have it as a reactant.
Aqueous ammonia is a weak base. And weak bases don't dissociate. Weak bases do something else. What do they? Well, all bases do this. Rather than dissociate partially, they do what? Hydrolyze. And so for all the bases, we always have to add water because bases don't dissociate, bases hydrolyze. And so we always have to have water as a reactant when we're dealing with bases, except for hydroxide. Is hydroxide and water just makes water and hydroxide. So, but for any other base, we have to add water as a reactant. And so this is just something we always do for bases. Because, and then when they hydrolyze, they form a little bit of ions. That little bit of ions can react in a metathesis or double replacement style reaction. Okay. But again, where the aqueous ammonia, don't worry about it for this test. Okay. Okay, other questions?
For this one right here, lithium oxide is added to water.
That one don't worry about either. That's called a Lewis acid-base reaction. So I skipped the entire. There was that part of the lab had lithium. What was it? Lithium oxide. Well, calcium oxide, magnesium oxide, and water. And so we're going to skip that. We'll talk more about acid-base reactions later, but that's an acid-base reaction. So you can just go ahead and skip that one. We're only having 3 types or 4 types of reactions, or 5 types, depending on how you count it. But the combination, the element plus an element makes a compound. Decomposition, the reverse of that. Single replacement, double replacement, and combustion. That's pretty much it. The other reactions that you'll see there are typically acid-base reactions or a combination of acid-base plus metathesis. Don't worry about those right now. So that's why I started going through the supplement, but the supplement has them all intertwined. So that's why I stopped doing the supplement. We just went. And that's why I said, for preparing for this test, look at the reactions we did in lab, single replacement, double replacement reactions that we did in lab are probably the best ones to do.
Chapter 8, forward number 55, lithium sulfide reacts with sodium phosphate. I got the right answer, but in the book it says it's lithium phosphate is
Insoluble.
But I was looking at my solubility rules, and based off of that, shouldn't it be aqueous?
Yeah, right. It should be aqueous based on group 1 salts are all soluble. Lithium has more exceptions. Do you know why lithium has more exceptions than fluoride? Lithium and fluoride have more exceptions in solubility rules. Do you know why? has to do with the size. So lithium, sodium, potassium, rubidium. And because of the small size, it has stronger Coulombic attraction. So there are more exceptions. This is why like chlorides, bromides, and iodides don't include fluorides, because there are a lot more exceptions for fluorides. There are exceptions for lithium as well.
Yeah, so the book, I don't know if it's a typo, but it says they
I know.
precipitate.
And so if we go to lithium phosphate, we can see what its solubility is here. I'm not, you know, actually, it's just not working. Normally, it comes up, but it hasn't come up here. Lithium orthophosphate. Exceedingly rare mineral. I don't want the exceedingly rare mineral, I just want lithium phosphate. Okay, that's probably why it's not coming up. I'm not saying that the book is necessarily wrong, that it's a typo. It could be that that's an exception. The reason why that might be an exception would be that lithium is very small in size, and then phosphate is quite high in charge, although it's pretty big. It's got a 3- charge, though. So this may be an exception, and bringing it, you know, still would be expected to be fairly soluble because of lithium, but there are a lot more exceptions for lithium salts that you're not going to have to memorize necessarily. There are even some sodium salts that are insoluble, like something like sodium, but it's more rare, although lithium phosphate I think would be more common, but it's not that common, I guess. But sodium uranyl acetate is actually insoluble. And so there are a number of salts that are actually insoluble, but it's not worth memorizing. And so the solubility rules I gave you are kind of the simplified version. It's just a rule, though. There's going to be exceptions to the rules, unfortunately. You just have to recognize it. And so something like this, high charge, small size, there are going to be more exceptions for.
For the activity series, are we gonna get that on the test? Are we gonna get like a copy of that?
You're going to get something like this for the activity series. It's going to be an upside down activity series. Lithium's at the top of the activity series. It's on the right hand side. So if you flip this upside down, that would be the activity series. Lithium at the top. That chart over there is the same as this chart, but this chart has been inverted. This is the way the charts used to be with the activity series on the left, but they stopped doing that. And so nowadays, the only chart that you see is fluorine's at the top on the left here, lithium's at the bottom right. upside down activity series. Okay, other questions?
You will, again, have some chemical reactions to do, and you want to just focus on the basic ones.
Are we gonna need to know, common names, like for instance, what sucrose is and, ethanol,
Methane, water, you'll have to
methane and
know.
water, and ethanol, you said?
Sucrose, you don't need to know.
So methane,
Methane, water, that's
okay.
basically it. Even ethanol, I'll probably give that to you. You don't have to memorize it. Although ethanol, is a big one. Common. But otherwise, ammonia, methane, ammonia, water. These are the common names you should know. Any other questions? Forgot to record this here, but if we look at the periodic table, we see that antimony is here, element 51. Do you see this bold zigzag line? The bold zigzag line means that this is in the boundary between metals on the left and nonmetals on the right. And so we call the elements that touch this the semi-metals or metalloids. And so antimony is a metalloid. It has properties intermediate between a metal and a non-metal. And we're going to react this with iodine. Iodine's a non-metal. What's the formula for iodine? I2. Yeah. Now, antimony, what would you suspect? What's the charge range for antimony? Let's take a look. What family is antimony? It's in the nitrogen family. Nitrogen family.
It's gonna be a 3.
It's going to be a 3 or plus 5. And so actually the common charges for antimony are 3 and 5. Those are the common charges here. But here you can see we formed antimony 3 iodide. So this is antimony in plus 3. Antimony is in plus 3. Then we can put 3 iodides on there. The other common one would be antimony 5 iodide. Now, antimony is borderline. Antimony, you can call it a metal or you can call it a non-metal. And so there are 2 common names for this. One would be antimony 3 iodide if we called antimony a metal. If we call antimony a non-metal, we would call this what? If we assume antimony is a non-metal, what would the name for this be? Antimony triiodide. So both names are very common for this. Antimony 3 iodide and antimony triiodide, because you can use either nomenclature rule. And people do. People use either one. And so antimony triiodide, then we need to balance this. So go ahead and balance. How many antimony? 2. How many iodines? 2, 3, and 2. Okay. Right, so this is the first step. The first step is we always have to have the balanced chemical equation in a stoichiometry problem. The next step is, okay, we're given amounts. If we're only given, let's say, the amount of antimony, let's say we're given X grams of antimony, and they didn't say anything about iodine, then what we do is we assume there's plenty of iodine to react. And vice versa. If they give us the grams of iodine, but they didn't give us any grams of antimony, then we just assume we have plenty of antimony to react. In this particular problem, they give us both. They give us antimony, 129 grams, and 381 grams of this. So 129 grams of SB and 381 grams of I2. When you look at this, do you know which one? There are three choices here. Choice one, this is stoichiometric. What does that mean? Stoichiometric means this is just the right amounts. So they just got this precise, and this is just the right amount of iodine to react with all that antimony. That's stoichiometric. Normally we do that in titration. Sometimes we do that in other reactions. More typically, we don't spend the time. More typically, one of these is limiting and one of these is excess. We'll have a little bit of leftover excess. And it depends on, which one's easier to clean afterwards or get rid of. Because we don't want the excess reagent contaminating our product. So, an additional step here. So can you look at this and tell me which one? One way, this is a mole ratio here. And so the comparison of moles method does this. It converts grams to moles and then compares. Do we have a 2-to-3 ratio or do we have something else? That's comparison of moles. And so for some people, they like that. It's easier. It's fine. I don't have anything against comparison of moles. It's just, why do that when we have to figure out this anyway? And so what we do is we do this. We do the smaller amount or theoretical yield method. And so in the first calculation, what we'll do is we'll go from grams of antimony to moles of antimony. And then from moles of antimony to moles of antimony 3-iodide or antimony triiodide. And then from moles of this to grams of that. All right, this is assuming all the antimony reacts. If all the antimony reacts, this is how many grams of product we should get. And then in the second calculation, we assume all the iodine reacts. If all the iodine reacts, then get this many moles of iodine, which will give us this many moles of SBI3, which will give this many grams of SBI3. All right, the next step is to choose the smaller amount. So this will be 3. Choose the smaller amount. What's going to happen is typically one of these is going to be bigger, the other is going to be smaller. And the smaller amount, the reason we choose that is because once all that reactant is consumed, that's how much we'll get, and there's no more reactant to react. So we choose a smaller amount that's equal to the theoretical yield, Ty, I'll call it, theoretical yield. And the reactant that produced the smaller amount is called the limiting reagent from the LR. So Ty's theoretical yield, LR is limiting reagent. So let's go ahead and do this calculation here. We'll do the first calculation. That is 129 grams of antimony. And then we'll look up the molar mass of antimony, which is 121.75. 1 mole weighs 121.75 grams of antimony. And so that gets rid of grams of antimony. That gets us to moles. And then the mole ratio. We have 2 moles of SBI3 for every 2 moles of SB. It's a 1-to-1 or 2-to-2 ratio. And then we need the molar mass of SBI3. And so SB is 121.75, and then we have 3 iodines. And it's going to be 3 times. Iodine is pretty heavy. It's 126.90 grams per mole. 126.90 grams per mole of I. This is not I2, it's I, because we just have atoms of iodine in there, not molecules. sat F2. The other thing is we can just look it up. You know, when you're doing the homework, it's easy enough to search it online. So 120, actually let's do 3 times 126.9 plus 121.75. This has a pretty high molar mass. 502.45 grams per mole. That's what we're going to use here. That's pretty heavy. So over here we'll do 502.45 grams of SBI3 per mole. The moles again. So let's see what we end up with here. I got 532. This is almost a mole of antimony. So I should form, that's actually a little more than a mole. And so I ended up with 532.370 grams. Okay, this is the yield from the antimony. And then what we're going to do is we're going to calculate the yield from the iodine. We're starting off with 381 grams of I2. And then the molar mass for I2 is just double this. So that's going to be, just do it in my head, but 126.9 times 2, 253.8. So 1 mole of I2 is 253.80 grams. Okay. And then 2 moles of SBI3. So 2 moles of SBI3 for every 3 moles of I2. And then the mass, 502.45 grams of SBI3 per mole of SBI3. So moles cancel. So give us so 381 divided by 253.8 times 2 divided by 3 times 502.45. 251.422 grams. This is our yield from the iodine alone. And so we choose a smaller amount, which would be this. This is going to be our theoretical yield of SB. And iodine will be our limiting reagent. Okay, once all the iodine has been completely consumed, we will only have made 251 grams. And so there's no way we could make the 532 because there's not enough iodine to react. So we have limiting reagent, antimony. The SB we call the excess reagent.
We got like double that.
You got to double that?
Yeah, me too.
Oops. All right, maybe I made a mistake here.
I have the same calculator. Maybe you just put something wrong in the calculator.
Yeah.
So I have the same setup.
Okay. What did you get?
503 grams.
503 grams? Okay, give me some more digits. 500.
502.855.
502.8?
Yeah.
All right, I guess we're only allowed 3 sig figs, so let's do 502.8 grams. Well, fortunately, that's still the limiting reagent. Is that what other people got? Yeah, okay. So 503 grams would be the yield. All right, we're going to do two more calculations. So this is your basic calculation. The two additional calculations we could do are this. We're not going to use all 300, or actually we're going to use all 381. We're not going to use all 129 grams of antimony. And so the next calculation is how much SB is consumed by the LR. How much SB is consumed by the LR is this is another stoichiometry problem. And so what we do is we start off with the LR, 381 grams of I2. And then we calculate stoichiometrically how much SB is required to react with that. And so we'll figure out 381 grams of I2, convert that to moles. 1 mole of I2 for every 253.80 grams. And then we're going to go to moles of SB. And so this was 2 moles of SB for every 3 moles of I2. And then we're going to go to grams of SB. And that was 121.75 grams of SB per mole of SB.
And let's see what that comes out to. Can you calculate that and know what you get? Okay, you get
121.8.
121.8 grams of iodine. We say iodine consumed by the LR. And so if we have 129 grams, we're going to consume about 113 grams.
Is it grams of iodine or antimony?
Or antimony, sorry, grams of antimony. So we have 129 grams of antimony. We consume about 113 grams. So how much is left over? This leftover is this unreacted antimony. And so we take the initial minus the amount consumed by the LR.
I got 121.8, not 112.8.
Oops, 121.8. So 122 roughly. Okay. Amount consumed by the LR, and this is going to equal, well, we'll round that to 122. So it would be 7 grams. So basically we're going to have 7 grams of antimony. That's going to be contaminating our product, SBI3. Both of those are solids. It turns into a separation problem, purification after that. So this is a standard limiting reagent problem here. Let's see what they did. So they calculate the yield from antimony, they calculate the yield from iodine, they pick the smaller amount. And then they got it. Theoretical yield, and then finally they had 7 grams of SP left over. Okay. Any questions on this?
To calculate how much antimony is consumed by the limit reactive, could you also go from grams yielded from the calculated from iodine, and then do a mass ratio to antimony?
So just saying, take the grams of iodine limiting reagent and then just do a mass to mass ratio.
No, take what you calculated from that equation, yeah, grams of the product, and then go back to antimony, and then
You could do that. That's fine. The only reason I don't do that is because that leads to more round off error. If you carried all the digits in your calculator and then worked it that way, then you'd get the same answer. But what most people do is they'll just round this and then they'll get a slightly different answer. Because, I mean, the given is 381, and we assume that it's right on, but here we have to round that usually.
Yeah.
So, but that's only disadvantage. Essentially, it should work just the same. Okay, any other questions? Yes. Right. Normally, the equations, like equation for antimony and iodine, are just balanced, mass balance or atom balance. We don't usually do an energy balance. And, mass and energy should be balanced altogether. And so in this part of stoichiometry, we're looking at the energy. And the way we balance energy, and we do it in different ways, but first, let's talk about the units of energy. The most common unit for chemists is the joule. It's spelled like this, Joule. That's given the symbol capital J, joule. It's based on physics. It's a kilogram meter squared per second squared. That's what a joule is defined as, 1 kilogram meter squared per second squared. It's equivalent to lifting a kilogram mass 1 meter high against gravity. There's another unit that's pretty common, that's calorie, abbreviated CAL. The calorie is based on heating water. It's the amount of energy required to raise the temperature of 1 gram of water by 1 degree C. So, how many calories? It turns out that you need more energy to heat up a gram of water by a degree C than you need to lift a 1 kilogram mass, 1 meter against gravity. About 4 times more energy to heat that gram of water. And so 1 calorie is defined as 4.184 joules. Okay? And so this is a common conversion for interconverting calories and joules, but mainly we use joules. A lot of these processes consume a lot of joules. And so kilojoules, kJ, is very common here. There's another calorie with a capital C. The calorie with a capital C is a food calorie. And the food calorie, if you look at ingredients like this here, this says 25 calories. This is a food calorie. But as far as chemical calories go, the relationship between a food calorie and a chemical calorie is that 1 food calorie is equivalent to 1,000 chemical calories. And so this is actually 25,000 calories. But who wants to be eating 25,000 calories, right?
And then who wants to call it a kcal, kilocalorie? Nobody wants. And so this is why there's food calories, and food calories are 1,000 times bigger than a chemical calorie. So these are just standard conversions. Standard conversions would just be dimensional analysis, converting from kilojoules to joules, joules to calories, this kind of stuff. So we'll do some of that. Now, what do we do with energy in balanced chemical equations? Usually we specify the energy using this symbol, delta H. This subscript R means reaction. So this is the energy change for that reaction here. But it's a special kind of energy. This energy is called enthalpy. Enthalpy is just like energy, but it has certain math type restrictions on it, certain restrictions, physical, on how you do it. And for example, you have to do it under constant pressure. This is why they don't call it just the energy. They call it the enthalpy because there's certain constraints. What we do. But most commonly, it's just known as the heat of reaction. But we have to be careful here. This is what this little asterisk. The little asterisk is not usually shown with the enthalpy or the heat of the reaction. It's just delta H. And oftentimes this R is omitted. We'll just call it delta H. If we read this asterisk, it says these terms may lead you to think that heat and enthalpy are the same. They are not. But the difference between them is beyond the scope of this introductory text. This is when we think maybe a better term for this would be energy of reaction when you do it under certain conditions to meet the requirement. And the energy, energy you can do things with energy. You can use energy to heat things up, or you can use energy to power things. So for example, if you get a gallon of gasoline, you can make a big fire, and that will heat up the air around there. Or you can use a gasoline in a car and go somewhere. And so that would be the energy of reaction. There's going to be a certain amount of energy available from that gasoline. And that energy can be, what we say, converted into heat and or converted into work. Usually, if you try to convert it into work, we end up with both heat and work. So here's a combustion reaction here. This is combustion of ethane. This is combustion of ethane yields CO2 and water and lots of heat. This heat of reaction is minus 2855 kilojoules. And so what this means is this: if I burn 2 moles of ethane, the negative means I'm going to release. And so I'm going to release 2,855 kilojoules of energy. What can I do with that energy? Well, that energy could go into warming a room, or that energy could go into powering something. It doesn't all have to get converted into heat. If you burn it and convert it all into heat, you're going to get the most heat. But if you burn it and do some work with it, like power some kind of motor or engine or something like that, then we're going to get less heat, but we're going to get more work. Work is just converting that energy into motion. There could be other types of work too. And so this isn't just, although we call that the heat of reaction, it doesn't necessarily all have to go to heat. Yeah. Now, the negative sign just tells us, are we losing that or are we gaining that energy? Energy is always positive. And so the negative sign means that's a product of this reaction. And so they did it over here.
where we see that this reaction produces this much energy. And energy is always positive. And so if it has a negative sign here in the delta H, then that means we add it to the product. If it is a positive sign on the delta H, then that means we add it on the reactant side over here. And so that would be shown in this next example here, where delta H is positive, that means heat has to be consumed. And therefore, if we look here, ammonia plus -2 kilojoules yields nitrogen and hydrogen. So that's the sign convention there. The sign convention is going to be associated with the delta H, but when you write it in the reaction, energy is always positive. It's like money down too. If this was minus $2,855, then the minus just means it's being exchanged in one way or the other, because there's no such thing as like a negative $100 bill. So when energy is released, things get hot. So you can see that here. When we take sodium hydroxide and hydrochloric acid, this is a double replacement reaction. We'll make sodium chloride and water and energy. And so they start off at 23 degrees, but they end up at 29 degrees because that heat is being released. And it's being released, that is produced in this reaction, that's going to warm everything up. And so that energy is being converted into heat in this case. So over here, we see the delta H is plus 178. That means we're consuming 178. We're not producing. And so that means the heat goes on the reactant side here. The energy goes on the reactant side. Right. So this is the reaction I talked about earlier that the Romans did. They took limestone, calcium carbonate, and baked it in their kiln to form the calcium oxide, which they used in concrete and CO2. How much energy was required to do this? 178 kilojoules for every mole of calcium carbonate. If I had, 2 moles, we double it. 3 moles, we triple it. The amount of heat. So this is what we call an endothermic reaction. Endothermic consumes energy. Over here, this would be an example of an exothermic reaction. Exothermic reaction releases energy. Yeah. So endothermic and exothermic. I talked about that earlier. So what we can do is we can use this as a conversion factor, just like anything else. So this is a 1 to 1 to 1 mole ratio, but for every mole of calcium carbonate, it's 178. For every mole of calcium oxide, it's 178. And for every mole of CO2, it's 178. So this gives us conversion factors that we can write out. This would be another example. If we burn 2 moles of ethane, we generate 3119 kilojoules. Where did that number come from? 3119 kilojoules. It looked like a different number earlier. When we burn 2 moles of ethane, this is saying we get 2855 kilojoules. That's ethane gas. No, here. There's a difference. I see what they did. Do you see what they did here? Because when I first looked at this, I was thinking 2855 is what they did. But then they have 3119. So can you see what is the difference? Because this is 2 moles of ethane burning, 7 moles of O2. What is the difference between these two? Why are we getting more heat in this one?
The H2O is a liquid, the first one's a gas.
Yeah. Up here, the H2O is a gas. Over here, H2O is a liquid. This is why This is why I'd like you guys to write it as H2O liquid, because eventually the steam has got to cool down. Have you ever gotten a steam burn? You know, when steam condenses, it releases a lot of energy, a lot of heat, causes some severe burns. And so what we like to do is we like to wait until the steam condenses back to a liquid and then figure out how much energy is released, because that hot steam cooling down is going to release more energy. And so when we do these combustion reactions, I always go to H2O liquid. I don't go to H2O gas because I want to wait for that to cool down. And it's going to cool down. You know, it's just a matter of time. And so this is why we use, when we do combustion, we go to H2O liquid, because H2O liquid is the favored state of water at room temperature, 25 degrees C. So that's what they're saying here. Water is a liquid at room temperature, 25 degrees C or 77 degrees Fahrenheit. And so this is where they got these conversion factors. If I burn 2 moles, I'm going to get this much. Or flip it over. If I got that much energy, I must have burned 2 moles. And so we add this into the stoichiometry map. This gives us an energy to mole conversion, or mole to energy conversion. And so if we start off with energy, and we have the delta H, then we have a direct way to go from energy to moles using that conversion. And so this adds a branch here to the stoichiometry map. Also a branch here, because if we know how many moles, then we'll know how much energy. So those are the energy conversion factors. And the rest of the stoichiometry map is the same as we saw before in the earlier chapter. And so just 2 additional branches here. All right. How many kilojoules of energy are released when 73.0 grams of ethane burns according to this equation here? And so we start off with grams of ethane, and then where are we going to go? We're going to go from grams of ethane to moles of ethane, and then from moles of ethane to kilojoules, because the conversion factor for that is 3119 kilojoules for every 2 moles. So that would be the remaining conversion factor. Let's take a look at what they did here. So they went from grams of ethane to moles of ethane. The molar mass is 30.07. And then from moles of ethane to kilojoules, 3119 kilojoules for every 2 moles of ethane burned. When they do it like this, they're assuming that there's plenty of oxygen to react, which we always do for combustion, but that's not always true. Here they're doing another combustion. Here they give us the delta H. 1 mole liquid water formed produces 286 kilojoules of energy. What quantity of energy is released when 15 grams of hydrogen burns in excess oxygen? So it's excess oxygen again. So we assume there's plenty of oxygen to react. And so this would just be grams of hydrogen to, actually this one's going to be a bit more, because we have to go from grams of hydrogen to grams of hydrogen to moles of hydrogen to moles of water, and then moles of water to kilojoules, because we have this conversion factor here. Or we could go direct. And so there are 2 choices for this particular reaction here. In the other one, we didn't really have this choice. In this one, we will have this choice. So if I combust hydrogen with oxygen, what forms? H2O. And so the first thing is we need to balance this. It's H2O liquid, because what I do is I start off at room temperature and then I wait until we reestablish room temperature. And that is, everything's cooled down. So balancing it, how many hydrogens? How many oxygen? How many H2O?
2.
And this is a gas here at room temperature. So they give us this. They say that for every 1 mole of liquid water, I get 286 kilojoules per mole of H2O liquid that forms. And so I could go from grams of hydrogen to moles of hydrogen, moles of hydrogen to moles of water to kilojoules. But I can also go direct from moles of hydrogen to kilojoules by doing this. That's 286 kilojoules per mole of water. How many moles of water do I form here in this balanced chemical equation? 2. And so if I do my delta H reaction here, this is not my delta H reaction. My delta H reaction, which has this little R here, is actually equal to double that. There are a couple of things here that I need to do. I need to double that because I'm forming not 1 mole of water, I'm forming 2 moles of water. And so that's going to equal 2 times that is what? 572 kilojoules. Okay, this is how we write it, the delta H. This delta H is for this reaction. Then I have to think, is this an exothermic or endothermic reaction? Is heat being released or heat being consumed or energy being consumed? Yeah, they tell us here, energy is released. If energy is released, then that means we're losing energy to the surroundings. The surroundings are going to get hot. And so all this energy has got to be dissipated here from this reaction. Usually, this is not always heat. There could be some light, sound, and in fact, this is pretty explosive, so there could be mechanical work, that is damage being done from the explosion, blowing up the container, etc. And so this isn't all heat, usually. So this is why the energy reaction is good. All right, when we see this, this is what we do with this. What this means is this. I'm going to get 572 kilojoules of energy released for every 2 moles of hydrogen, or minus 572 kilojoules for every 2 moles of hydrogen. The minus just tells me we're losing rather than consuming the energy. But the negative sign's tricky in stoichiometry because let's say you get, if you left the negative sign there and you got negative 10 grams of hydrogen, is there such thing as negative 10 grams of hydrogen? No. And so this is why sometimes we write the negative sign, sometimes we don't. We can do this in terms of oxygen. In terms of oxygen, it would be 572 kilojoules released for 1 mole of oxygen, or negative. And we can do this for water. For water, it would be 572 kilojoules released for every 2 moles of water, liquid. Well, that's the same as this ratio here, if we divide it by 2. So they're all consistent with one another. And so in this case, I would have went from grams of hydrogen, 15 grams of hydrogen, 15 grams of hydrogen to moles of hydrogen, and the mole of hydrogen just straight to kilojoules using this. And so the delta H, when you see the delta H written next to an equation, it's for the mole ratios that are given. And so here they give us our delta HR per mole of C8O. Okay, this is for per mole of CH18. We have to look at what the balanced chemical equation shows us here. They do the balanced chemical equation. We didn't do the balanced chemical equation here. This is the first thing we need to do. Okay. So let's look at some problems. So the mass-to-mass stoichiometry, this is pretty much what you're going to have. And unfortunately, my book is different. Your book is section 10-3. My book is section 10-2. Did you have any questions about mass-to-mass? Do you want me to do some more examples of mass-to-mass stoichiometry? Something that's going to be on the test. There's going to be a mass-to-mass stoichiometry on the test. So, I don't know.
Is that section 10.3, right?
Yeah. Did you try any of the problems?
Yeah, I tried the one that said it on, so I could review.
Okay. Any in particular that you guys had questions on? We could do it in the context of maybe percentage yield. Yeah. 4.14 grams of butane reacts with excess oxygen. This reaction yields 11 grams of carbon dioxide. What is the percentage yield of this reaction? Butane C4H10. You should be able to derive this equation here. They gave it to us. So mass-to-mass stoichiometry is grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. And that's what we're going to call the theoretical yield. That's going to be the theoretical yield because we have excess oxygen gas, pretty much an unlimited supply of oxygen. And so this will be the limiting reagent. This will dictate the yield, the theoretical yield. And so butane, these are common. Carbon, hydrogen, oxygen, nitrogen. These are very common in organic chemistry. So it's useful to have those memorized so you can calculate the molar masses quickly. So if we have 4 carbons, it's 4 times 12.01. And then we have 10 hydrogens. That's going to be 10 times 101. And so that's going to be, what is that, 4804 plus 1010 is 5814. So 1 mole of methane, or not methane, butane, the naming, the aim, just, they're all going to be similar to methane. They're hydrocarbons. But they have different amounts of carbon. Like but means 4 carbons, meth means 1 carbon, eth means 2 carbons, prop means 3 carbons. And so this is just butane. 4 carbon, hydrocarbon, 5814 grams butane. So this gets us our moles of A. So grams of A to moles of A. Now we go to moles of B. So what should be our B in this particular problem? What are we interested in? Is it the oxygen? No. Yeah, carbon dioxide. Sometimes we're interested in the oxygen because we want to know how much oxygen we really need. In this case, they're interested in the CO2, so we'll do that. And it's going to be 8 moles of CO2 for every 4 or 2 moles of butane, C4H10. So we did our moles of A to moles of B, and then moles of B to grams of B. So oxygen's easy because it's 1600. So 2 oxygens is going to give us 3200 plus carbon is 1201. So it gives us 44.01 grams of CO2 per mole of CO2. So grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. So what does that come out to? So I'll punch that out.
12.5.
12.5? Okay, this would be our theoretical yield. Since we have excess oxygen, the yield from oxygen will be much, much larger. And so this is our theoretical yield. Our limiting reagent is butane. Smaller amount. This would be our limiting reagent, LR. Our percent yield is equal to the what? Kind of have to have this memorized. Actual yield by theoretical yield. So if the actual yield were the same as the theoretical yield, you'd get 100% yield, which is correct. You would expect 100% yield. And so in this case, the actual yield was only 11.0 grams. And the theoretical yield was 12.5 grams, and then times it by 100%. This would give it 12. And so this would be a standard mass-to-mass stoichiometry problem, a limiting reagent problem, and a theoretical yield problem, all combined in one. Let's look at this limiting reagent conceptually. Here you can look at it based on these and figure out which one's limiting, which one's excess, or if it's stoichiometric. This one looks a little bit tricky. Let's look at this one, 44. The flask below illustrate 3 trials of reaction between varying amounts of zinc and a constant volume of hydrochloric acid solution of constant concentration. The table gives the initial amount of zinc added and the observations of the conclusion of each reaction. So if you look at flask 1, do you see this stuff here? What does that look like at the bottom of the flask? It looks like zinc, doesn't it? Zinc is this kind of spongy kind of metal, like zinc. And this is the conclusion of the reaction. So this tells us there's some leftover zinc here, which means that the zinc must be the excess reagent. The hydrochloric acid, there wasn't enough hydrochloric acid. Because when hydrochloric acid reacts with zinc, it makes hydrogen gas. And you guys tested the hydrogen gas using the match. And so this is a lot of hydrogen gas today. We probably don't want to test this with a match. There. Here, flask 2, it looks like there's no zinc. So all the zinc reacted. Flask 3, There's no zinc there. All the zinc reacted. So flask 3, you could say something here. In flask 3, all these started off with the same amount of hydrochloric acid. And so in flask 3, we can say that the limiting reagent must be the zinc. Yeah. In flask 2, this could be stoichiometric. Flask 1 is definitely a limiting reagent to excess reagent problem. And so let's look at their table that they have. Oh, they added different amounts of zinc here. So the reaction produces an aqueous solution of zinc chloride and hydrogen gas. Explain the observed results. So they added 6.1 grams of zinc, balloon inflated completely. Someone reacted, zinc remains, so excess zinc. They added 2.37, balloon inflated completely, no zinc remains. So this one, either hydrochloric acid was in excess or it was stoichiometric. And this one is what we said earlier. Okay, but most limiting reagent problems are going to be like this here. On 45. A solution containing 1.63 grams of barium chloride is added to a solution containing 2.40 grams of sodium chromate. So the reaction between barium chloride and sodium chromate makes what? Yeah, sodium chloride and barium chromate. Barium chromate's a precipitate. Chromates, phosphates, and carbonates are all insoluble except for group 1 and ammonium. And so we get a precipitated barium chromate. But how much precipitate do we get? Well, that depends on the limiting reagent here. We don't know which one's limiting, which one's in excess. And so we have to try to figure that out. And so we do it by the smaller amount method. We calculate the yield from this, the yield of barium chromate precipitate, and we figure out the yield of barium chromate precipitate from this. And then pick the smaller amount. Let's take a look. We're just looking at the basic setups here. Carbon dioxide can be removed from air by reaction with potassium hydroxide. So this is what we call Lewis acid-base reaction. I haven't talked about this. You're not responsible for predicting this sort of reaction. But we did kind of see it earlier with barium hydroxide, not potassium hydroxide. If 15.6 grams of carbon dioxide reacts with 43.0 grams of potassium hydroxide, what mass of potassium carbonate will be formed? So again, limiting reagent. So you'll go through and calculate the yield from each of these and pick the smaller amount. Except this one has an additional. The small amount will be the theoretical yield, and that's how much should be formed here. What amount of excess reactant remains after the reaction is complete? So we have to do 2 additional calculations. We have to figure out how much of the excess reagent is consumed by the limiting reagent, and then we have to calculate how much excess reagent is left over. And so basically all the calculations we did earlier. The equation for one method of preparing iodine is this. This is a redox, a more complicated redox reaction, not single replacement. There are other kinds of redox reactions that we do. There's 6.00 kilograms of sodium iodate, which is this, is reacted with 7.33 grams of sodium hydrogen sulfide, which is this, or sodium bisulfite. How many kilograms of iodine can be produced? So again, calculate the yield from each of these for iodine. Smaller amount will be the theoretical yield. Which reactant will be left over and how many kilograms will be left? So the same type of calculation we did earlier. Carbon monoxide is the chief waste product of gasoline combustion process. Auto manufacturers use catalytic converters to convert carbon monoxide into carbon dioxide. So CO plus O2, we can burn it further. When 12.6 grams of carbon monoxide is allowed to react with 5.22 grams of oxygen gas, how many grams of carbon dioxide are formed? What amount of the excess reactant remains after the reaction is complete? It's the same calculation. A mixture of tetraphosphorus trisulfide and powdered glass is in the white tip of a strike anywhere match. The P4S3 is made by direct combination of the elements. 8 P4s plus 3 S8s yields 8 P4S3s. If 133 grams of phosphorus is mixed with full contents of a 126 gram bottle of sulfur, how many grams of the compound can be formed? how much of which element will be left over. So exact same calculation here. And finally, this one, sodium carbonate can neutralize nitric acid by the reaction. So 135 grams of sodium carbonate here. Sodium carbonate, what does this make? So nitric acid plus sodium carbonate is going to make hydrogen carbonate, but we don't call it hydrogen carbonate, we call it what? H2CO3, which is called carbonic acid, and carbonic acid decomposes spontaneously to H2O and CO2. So this is our hydrogen carbonate and sodium nitrate. Well, sodium nitrate is not going to decompose, it's going to be here. This is another double replacement type reaction. And then they give us both amounts and ask us how many grams of carbon dioxide will be released in the reaction. So the same kind of calculation that we did earlier. If we look at the energy calculations here, this is a kilojoule. I would do how many kilojoules are equivalent to this? 0.731 kilocalories, kcals. So 0.731 kcals would be 731 calories. 731 calories we convert to joules, 4.184 joules per calorie, and then convert it to kilojoules. What number of calories is the same as 651 joules? Etc. And so these are just basic conversions. Do you want me to do any of those? Maybe we'll do number 54 here, because this deals with a food calorie here. Lemon meringue pie contains 333 calories a piece of pie. This is just to emphasize the difference between a food calorie and a regular calorie. So number 54 is, if we had 333 food calories, which has a capital C, then we know that there is 1,000 little calories for every big calorie. And they want us to know how many joules and how many kilojoules. So this would be 333,000 little calories. And then a lot of people have this memorized. It's 4.184 joules per little calorie. So how many joules does it count to? Do you have it?
Yeah.
What did you get?
1,393,272 joules.
$1,393,272.
272.
Okay, to figure out how many kilojoules, well, we can just multiply it or move the decimal. This would be 1,393 kilojoules. 1,393 kilojoules. I'm moving the decimal to the other.
Should we know that conversion for the midterm?
This one, no. You don't need to know this conversion for the midterm. We're not doing, we're only doing mass-to-mass stoichiometry for the midterm. And so these aren't there.
Question. So which combustible fuels do we need to memorize? You said butane.
You don't need to memorize any of them.
Oh, okay. I thought you said we do need to have a formula for butane.
No, you don't need to know the butane. I was just saying, methane has 1 carbon, ethane has 2 carbons, propane's 3 carbons, butane's 4 carbons.
So if that's on the fence, we'll do that.
No, you don't need to know that. It's just if you're curious. Energy is transferred from sunlight in the photosynthesis reaction with carbon dioxide and water vapor combined to produce sugar and release oxygen. The amount of energy is 2.82 times 10 to the third kilojoules per mole of sugar. So we'll give this one a try here. Although that one's in the book. We should do something. But that's a pretty good one. So we'll take a break right now and then we'll start after the break. So were there any questions? Get started. All right. When you look, there are 2 ways that the energy is going to be written. It's either going to be written in the equation like this, which is nice. So this would be endothermic. Energy is a reactant. This would be exothermic. Energy is a product. But this isn't the common way it's written. This is nice because it's easy to see here. Again, exothermic. The typical way it's written is like this, delta H. So we have delta H is minus 75.8. That's for this. So that means this is a reactant or product? Product. And so we just have to make sure we do that as a product. When 10.1 grams of sulfur reacts with excess carbon monoxide, what quantity of energy expressed in kilojoules is transferred? And so we'll take a look at this one here. We'll do that, number 66. So we have 10.1 grams of sulfur. What we want to do is we want to go from grams of sulfur to moles of sulfur. Look up the molar mass is 32.07 on this. So 1 mole of sulfur is 32.07 grams. It's 32.06 in your book, but we'll just use this one here. And so we have that, moles of sulfur. And then we look at this. This is for the reaction as written. So when we look at the reaction as written, it's per mole, 1 mole of sulfur. If this is the reaction as written and this were 2, then this amount of energy would be for 2 moles of sulfur. So for example, here it's 75.8 kilojoules released for every mole of sulfur that's combusted, 75.8 kilojoules released for every 2 moles of carbon monoxide reactants, and 75.8 kilojoules released for every 1 mole of SO2. And 2 moles of carbon in this case, since that was on the end. And so here, we're going to see that it's going to be 75.8 kilojoules. And then rather than writing the negative here, I'll write release. Or I could write the negative there per 1 mole of sulfur, S. So that will give it to us. Alternatively, if I wrote negative 75.8 kilojoules here per 1 mole of sulfur, then my answer would come out negative, and then I would just interpret that as being released, energy release. So that's what we do with this line. All right, let's take a look at number 67. What mass in grams of octane, the component of gasoline, would you have to burn in your car to transfer 9.48 times 10 to the 5 kilojoules of energy? So didn't finish this calculation here. Maybe we should finish this. So this is 10.1 divided by 32.07 times 75.8. This gives us 23.87 kilojoules.
Here it gives us negative 23.87 kilojoules. And since we don't have the negative sign up here, we say kilojoules. We don't know if it's released or consumed. And so we write released here. This negative sign here just means we must have lost that. And so we don't have to write the word released there. So now when we look at number 67, there are two ways to handle number 67 as well. One where we keep track of the sign. And so what they want is they want 9.48 kilojoules. 9.48 times 10 to the fifth kilojoules of energy. We have a delta H of minus 1.09 times 10 to the fourth kilojoules. And so the two ways we can do this is they want this, and that means that energy has to be released. So either we change the sign here, that means we need 9.48 times 10 to the fifth kilojoules of energy released here. And then what we see here is that for every 2 moles of octane, C8H18, we get minus 1.09 times 10 to the fourth kilojoules. And so the negative will cancel out the negative. So both of these are energy being released here. And then they want the grams. And so we'll need the mole mass of octane. The mole mass of octane is 8 times 12.01 is 96.08 plus 18.18. 18.18, which would be the hydrogen. And that's 114.26 grams of octane per mole of octane. And so times 2 times 9.48 times 10 to the fifth divided by 1.09 times 10 to the fourth. And I get 19,874.9 kilojoules, or not, sorry, grams. 19,874, so 19 kilograms. Or we do this, 9.48 times 10 to the fifth kilojoules needed, and then 2 moles of octane for every 1.09 times 10 to the fourth kilojoules released. And so I'll just change the sign, and then this would be the same, and we get the same answer here. I have to change the sign because if I leave one of these negative, then I'm going to get a negative grams. Negative grams makes no sense at all. So we have to just pay attention to the sign. And those are the two common ways that we pay attention to the sign in energy stoichiometry. Okay. Any questions on energy stoichiometry? No? All right, the next thing we're going to do is we're going to add one more branch to the stoichiometry math. So the heart of the stoichiometry math is, let's say, mass of A to moles of A conversion, and then moles of A to moles of B, moles of B to mass of B. When we look at the mass of A, this has to be the mass of pure A. What we can have here is we can have an extra branch in our stoichiometry math. And the extra branch would be the mass of a mixture of A. So if we have a mixture of A, then we have to go from grams of A mixture to grams of pure A. Likewise, here, sometimes we have the mass of B, and sometimes we want the mass of B mixture. And so we might add a branch here too. If we know the percent composition of the mixture. So a common problem would be like air. If you have the mass of air is a mixture. And usually what we need in air is the oxygen. So we might start off with, let's say, 100 grams of air. How many grams of oxygen is that? And so we go from mass of air to mass of pure oxygen. We need to know the percent composition. And then once we're at mass of pure oxygen, then we can calculate whatever else we need. Or sometimes we end up with mass of pure oxygen here at the end. And we're getting the oxygen from air. So if we need, let's say, 20 grams of pure oxygen, how many grams of air do we need? And there we need the percent by mass composition. So if we have the percent by mass composition, we can deal with mixtures. And so that's what number 77 here is. Number 77, a phosphate rock core yields a rock that is 79.4% calcium phosphate, the raw material used in preparing calcium dihydrogen phosphate, the fertilizer known as superphosphate. The rock is made to react with sulfuric acid according to the equation here. What is the smallest possible mass of rock in kilograms that must be processed to yield 0.500 tons of fertilizer? And so this is where we're going to have the mass of A, pure A, going to moles of A to moles of B to mass of B, and then mass of B to mass of mixture. The mass of mixture will be the rock that's used. Well, they should call it the ore something. Oh yeah. So here, first off, 79.4% calcium phosphate. Calcium phosphate, do you know the formula for calcium phosphate? Actually, they give it to us here. C3PO42. Now, rocks are made up of minerals. This would be a mineral. Mineral is a pure substance. And so this is by mass. And so what this means is we're going to have 79.4 grams of pure calcium phosphate for every 100 grams of the ore, what they call the rock. The rock is going to be a mixture of different compounds in there, of which looks like calcium phosphate is a major component of this rock. And so we have 0.500 tons of fertilizer. The fertilizer is superphosphate, which has the formula CaH2PO4, 2. So we want 0.500 tons of this pure substance. So this is going to be our A. So we're going to go from tons to what? I'm going to go from tons to is it a metric ton or a regular ton? Do you know how many pounds are in a ton? 2,000 pounds in a ton. So we'll just go, I'm pretty sure this is English, so we'll go 2,000 pounds in a ton. You don't have to have that memorized. Do you know how many grams are in a pound?
453.59.
We'll go with 453.6 grams per pound. You don't need to know this, those will be given. So we have tons, cancel, pounds cancel, that gives us grams of product, grams of A. So we go from grams of A to moles of A. And so we'll need to know the molar mass of this. Ca H2PO4 2, which is going to be a little bit of work here. Calcium mass is 40.08. And how many calciums do we have? One. So that's 40.08. How many hydrogens do we have? 4 hydrogens. That's going to be 4.04. 2 phosphorus, which will be 2 times, we have 30.97. So 61 point. $91.94. 61.94. How many oxygens? 8 oxygens. So that's 8 times 16, 128. And then just add it up. $234.06. Yeah. So 234.06 grams per mole of the fertilizer, calcium dihydrogen phosphate. Name this. So we go from grams of A to moles of A, the moles of A to moles of B. So the moles of B is going to be calcium phosphate. And the mole ratio here is 1 mole of calcium phosphate for every 1 mole of calcium dihydrogen phosphate. So it's a 1-to-1 mole ratio. So 1 mole of calcium phosphate for every 1 mole of calcium dihydrogen phosphate. Then from moles of B to grams of B. And so calcium dihydrogen phosphate was this. Calcium phosphate, we're going to have 3 calciums. So 3 times 40, 120. And 3 times 8 is 20. 4. 120.24. 2 phosphorus. Here 61.94. 8 oxygens. 128. So I'm going to have 120.24 plus 61.94 plus 128. 310.18. 310.18 grams of pure calcium phosphate, Ca3PO42, per mole, Ca3PO42. So I go from grams of A to moles of A, moles of A to moles of B, moles of B to grams of B, but this is grams of pure B. We have a mixture though. And this is our mixture here. And so what I'm going to do is I'm going to cancel out the calcium phosphate. So I'm going to have 100 grams of rock for every 79.4 grams of calcium phosphate. So there's just one extra step here, basically. And this is going to give me grams of rock, but they don't want grams of rock. They want tons of rock? No, they want kilograms of rock. All right, so if we're going to go to kilograms of rock, then we'll just convert this into kilograms. 1 kilogram is equivalent to 1,000 grams. Okay, so that's to give it to us. So it's 0.5 times 2,000 times 453.6. Screw that up. Try that again. 0.5 times 2,000 times 453.6 divided by 234.06 times 310.18 times 100 divided by 79.4 divided by 1,000. I got 757.0 kilograms, or 757 kilograms of rock. All right, so that's one with percentage. Let's take a look at number 78 and see what we have here. 78 is carborundum, is silicon carbide. It is widely used as an abrasive in industrial grinding wheels. It is prepared by the reaction of sand, silicon dioxide or silicon peroxide, with the carbon and coke. Coke is just a form of carbon. And so SiO2 plus carbon yields silicon carbide plus carbon monoxide. What mass in kilograms of carborundum can be prepared from 727 kilograms of coke? That is 88.9% carbon. And so here, we don't have pure carbon. We have 727 kilograms of carbon mixture. And so we'll go from kilograms of carbon mixture to grams of carbon mixture, grams of carbon mixture to grams of pure carbon. That is, it's 88.9 grams of pure carbon for every 100 grams of carbon mixture. And then grams of pure carbon to moles of pure carbon, moles of pure carbon to moles of silicon carbide, and then moles of silicon carbide to kilograms of silicon carbide, carborundum. And so that's using the percentage at the beginning. Here we're using the percentage at the end. We use it at the beginning, it's not inverted or flipped like that. A sludge containing silver chloride is a waste product from making mirrors. The silver may be recovered by dissolving the silver chloride in sodium cyanide solution and then reducing the silver with zinc. The overall equation is this. What minimum amount of sodium cyanide is needed to dissolve all the silver chloride from 40 kilograms of sludge? That is 23.1% by mass silver chloride. So here we have 40.1 kilograms of silver mixture. And so we'll go from kilograms of silver mixture to grams of silver mixture, grams of silver mixture to grams of pure silver. It's 23.1 grams of pure silver per 100 grams of mixture. And so it's the same, 78 and 79, the same setup, which is different. Both of these have the percentage at the beginning of the stoichiometry problem. Okay, this is a mixture problem here. This one, okay, skip that one. This is another one. This one's tricky because this one they give you 2 percentages. One percentage is the 61% yield. That's the average yield by mass. The other percentage is a mixture. And so this one we have to deal with the 2 percentages separately. Keep track of it. And so this one's a bit more challenging here. Actually, that one, we'll skip that one too. All right, so those are some examples of stoichiometry problems. Yeah. There's one more problem I'd like to do from this, and that's number 87. Number 87 is the student was given 1.6240 gram sample of a mixture containing sodium nitrate and sodium chloride, and was asked to find the percentage of each compound in the mixture. She dissolved the sample and added a solution that contained an excess of silver nitrate. The silver ion precipitated all the chloride ion in the mixture as silver chloride. It was filtered, dried, and weighed. Its mass was 2.056 grams. What was the percentage of each compound in the mixture? So this is number 87. Number 87, we have a sample here, and it's 1.6240 grams. Mixture. And then what we want to do is we want to determine the percent of each compound. It's going to contain sodium nitrate and sodium chloride. Then they're going to treat this mixture with silver nitrate. Only the sodium chloride reacts. The sodium nitrate, there's no reaction. And so the sodium chloride reacts with silver nitrate to precipitate out silver chloride, and we'll have sodium nitrate left over spectating. With the reaction here, it ends up giving 2.056 grams of pure silver chloride from this. Okay, so what we can do is we can go from grams of A to moles of A. And then from moles of A, we can go to moles of B, which will be sodium chloride. And then from moles of B, we can go to grams of B, which would be how many grams of sodium chloride we have. If we know how many grams of sodium chloride we have, then the rest must be sodium nitrate here in the mixture. And so the thing we're going to calculate here is we're going to calculate the percent sodium chloride. Here. The percent sodium chloride would be the grams of sodium chloride, which will be B, divided by the grams of mixture, 1.6240 grams of mixture, times 100%. So we're going to take this grams of B and then plug that in here. And then we can calculate the percent. If we know the percentage of sodium chloride, then the rest must be sodium nitrate. So let's say it's 50% sodium chloride, then it has to be 50% by mass sodium nitrate because there are only two things in the mixture. All right, so this is a multi-step problem. And so the first thing is to figure out how many grams of B there are, that is the sodium chloride. So we'll start off with the grams of A here, 2.056 grams of silver chloride. So 2.056 grams of silver chloride was produced. And then we're going to go to moles. And so I'll need the molar mass of silver chloride.
Well, after you do a bunch of these molar masses, you might get tired of calculating it, so we'll just look it up online and see what it is. 143.32 grams per mole.
So 1 mole of silver chloride, 143.32 grams. So we go from grams of A to moles of A, and moles of A to moles of B. In this case, our moles of B will be sodium chloride because that's part of the mixture. And so it's a 1-to-1 mole ratio. 1 mole of sodium chloride for every 1 mole of silver chloride. And then we'll look at the mass of sodium chloride.
NaCl. 5844
Grams per mole. So 58.44 grams of sodium chloride for every mole of sodium chloride here. And that leaves us with grams of sodium chloride. So let's go ahead and calculate that.
We have 2.056 divided by 143.32 times 58.44.
We use 0.838. How many sig figs am I allowed? In this case, I'm allowed 4 sig figs. So 0.83835 grams of sodium chloride. And therefore, I'm going to calculate the percent sodium chloride next, which is going to be 0.83835 grams of sodium chloride over 1.6240 grams of mixture times 100%. So this comes out to 51.622% sodium chloride. And then I'm going to take 100 minus this. Oops. And that means the percent sodium nitrate must be the balance. That is 100% minus 51.622%, which is going to give me 48.377% sodium nitrate. And so 51.62% sodium chloride, 48.38% sodium nitrate. I'm rounded. Oftentimes, we don't care what the other components of the mixture are. And so most of the problems like this aren't 2-component mixtures. Most of the problems like this, they say that this is other stuff. And the other stuff doesn't react. And so we're just interested in how much sodium chloride, which was the reactant in this mixture, as long as the other stuff doesn't react. Well, we know that the other stuff in this case, the sodium nitrate, won't react. And so typically when we do a problem like this, we're just interested in how much of the stuff that reacts is in that mixture, and it's only 51.62. This extra step is typically not done. So this is the percent other stuff, 48.377% other stuff. It just so happens in this case, we know what the other stuff is. But on most of the problems like this, it's not given what the other stuff is. It's just the other stuff that doesn't react. And so, So number 88 would be an example of that. A researcher dissolved 1.382 grams of impure copper. Impure copper contains other stuff. What is that other stuff? They aren't telling us what the other stuff is. It's just other stuff. In nitric acid to produce the solution of copper 2 nitrate, the solution went through a series of steps in which the copper 2 nitrate was changed to copper 2 hydroxide, then to copper 2 oxide, and then to a solution of copper 2 chloride. This was treated with an excess of soluble phosphate, precipitating all the copper in the original sample as pure copper 2 phosphate. The precipitate was dried, weighed, and its mass was 2.637 grams. Find the percentage mass of copper in the original sample. So this one's a bit more tricky because there are a whole bunch of reactions that occur here, but they don't tell us what the reactions are, at least the balance reactions here. But what they do tell us is that all the copper that was in this original mixture ends up in this here. And so we don't lose it. So number 88 is a tough problem. Let's take a look at this here. So we have 1.382 grams of mixture. This mixture contains pure copper solid plus other stuff. And the other stuff, one thing we need to know about the other stuff is it doesn't react. And so it's inert. Doesn't react. So all this went through a whole bunch of steps and then ends up at copper 2 phosphate. Like this, solid. So all the copper in the original sample here ends up here. No copper was lost. So assume no copper was lost. If we assume that no copper was lost, then what we can do is this. We can go from we know the grams of this. So we have 2.637 grams of copper 2 phosphate here. So we can go from grams of copper 2 phosphate to moles of copper 2 phosphate. And then what we're going to do is we're going to go from moles of this to moles of pure copper. The mole ratio that we're going to use for this is this. For every one of these, we had to have 3 coppers. And so that means there are 3 moles of copper that end up in every 1 mole of copper 3 phosphate. So rather than knowing what all these steps were, I mean, we have so many different reactions here, we just say that all the copper ends up in the compound. If all the copper ends up in the compound, then we must have 3 moles of copper for every 1 mole of that compound. Once we get that, then we can get the grams of pure copper solid. And if we have the grams of pure copper, then the percent copper in the mixture is equal to the grams of pure copper that we had over the grams of mixture, 3.82 grams mix times 100%. In other words, the percentage is going to be the percent of A is equal to the grams of A over the total grams. So this is going to be a 2-step calculation. The first step is to figure out how many grams of copper we have. So we'll use some stoichiometry for that. It's going to be 0.37 grams of copper, pure copper phosphate that was precipitated, Cu3PO4 2. Okay, what's the molar mass of Cu3PO42? I don't want to calculate that. And so I'm just going to look that up. Copper phosphate. Copper 2 by far is the most common. So if I type in copper phosphate, I'll likely get copper 2 phosphate here, 350.58 grams per mole. And so 1 mole of Cu3PO42 weighs 380.58 grams. So the grams cancel, it gives us moles of copper 2 phosphate. And then the next thing is this conversion here. This conversion is tricky because I made the assumption that all the copper in this compound came from pure copper metal. And so 3 moles of pure copper metal for every 1 mole of Cu3PO42. And that just comes from the formula. The formula has 3 coppers for every one of these units here. And then we have the molar mass of copper, which is 63.55 grams. 63.55 grams of copper for every mole of copper. And so this is going to give us some grams of pure copper here. So we'll do 2.637 divided by 380.58 times 3 divided by, or no, times 63.55. 1.320. 1.320, and I'm allowed one more, 9. I'm not allowed one more, but I have one more, 9 grams of copper. And so plugging that in over here, I have 1.320, so 9 grams of copper in this 1.382 gram mixture times 100%. So I'll take that and divide it by 1.382 times 100, gives me 95.58. It's like 4 sig figs throughout. 95.585% copper. 95.59% copper in that mixture. And so this was impure copper. It just turned out to be about 95, 96% copper. All right, so those are some typical challenge problems with stoichiometry, all of them dealing with percentages. All right, any questions on this? Here are some of the chemicals that we found in this chapter. Can you name these?
Magnesium to
Magnesium hydroxide, yeah. Magnesium is fixed charge. We don't need Roman numerals for that. We know these. What's this one? Yes, happens to work at it. How about this one? This one looks a bit more fun. Yeah, potassium bisulfate or potassium hydrogen sulfate.
Potassium sulfate,
Okay.
sodium hydroxide.
Phosphoric acid is what we named that. This one, ammonium chloride, good. Ammonia, hydrochloric acid, magnesium. This is magnesium. Yeah, we already had that one. We had KOH also, but this one we did. Magnesium nitrate. Hydrobromic acid or hydrogen bromide. Depends. If it's a gas, it looks like they're looking at formation in the element, so it could be hydrogen bromide. If it's in the gaseous, if it's in the aqueous state, hydrobromic acid. Hydrogen formed from hydrogen bromine. Sodium sulfate. Sulfuric acid. Right? Nitrite would have a negative charge. This has no charge. Nitrogen dioxide.
Sodium chromate.
Yeah, sodium chromate, barium chromate.
Calcium phosphate.
Calcium phosphate.
Sodium phosphate.
Sodium phosphate.
Silver nitrate.
Silver nitrate. That's the stuff that stains your fingers black. Silver chloride.
This is like a female.
Okay, let's symbolize.
Since we're moving on, that was stoichiometry, and then we're revisiting the atom. This is atomic theory part 2. And we have to revisit the atom because we need to know about the properties of atoms. In order to better understand the properties of the atoms, we need to know the structure a little bit better. And so in atomic theory part 2, we're looking at what's happening with electrons in the atoms. This is an MRI scan here at that. In order to understand what's happening with electrons, we have to understand light. Light is also called electromagnetic radiation. Electromagnetic radiation consists of oscillating electric fields and oscillating magnetic fields. This transfer of light. And so here we can see an oscillating field. Oscillating just means it's going up and down. And so this could be the electric field. The magnetic field would be perpendicular to it. Here. But we don't really have to know that. What we do need to know is that this is moving. And do you know how fast light moves? Light moves at the speed of light. Do you know what the speed of light is? The speed of light is this, 3.00 times 10 to the 8 meters per second. Light is moving very fast. If you convert this to miles per hour, it's 186,000 miles per hour. That's how fast it moves in a vacuum. We have lots of different kinds of light. They all differ based on their frequency and wavelength. The frequency is how fast it oscillates. So if this is moving, they're all moving at the same speed. And so gamma rays are oscillating very fast, whereas long radio waves are oscillating much slower. And so we say that gamma rays are higher frequency or high frequency light, whereas long radio waves are low frequency light. But when we look at the frequency is still very fast. Frequency is given in units of hertz, which is abbreviated capital Hz. Frequency has a symbol called mu, which is this V there. And 1 hertz is defined as 1 cycle per second. And so what we do is we start off here at the top of the hill, and as this moves past us, we drop down to the bottom and then go back up to the top. So that would be 1 cycle. So we start here, drop down, come back up because this thing is moving at us very fast. So long radio waves have frequencies of about 1 cycle per second to, let's say, 10,000 cycles per second. Whereas when we look at gamma rays are looking at 10 to 24 cycles per second. So it's oscillating extremely fast. So we see many, many orders of magnitude difference. In terms of the wavelength, it's hard to see. The wavelength is the distance between one peak to the next, or one trout to the next trout. And so when we look at long radio waves, the wavelengths are quite long. This is 1 million meters here. This would be 100 million meters. And so 100 million meters from one peak to the next. But it's moving so fast, it can oscillate like 100 cycles per second or 10,000 cycles per second. Whereas over here, we're looking at 10 to the minus 16, 10 to the minus 14, 10 to the minus 12. What's significant about all these is that the wavelength here, that is the peak-to-peak distance, is smaller than the atom. The atom is about 10 to the minus 10 around here. This would be even shorter than the diameter of the atom. Okay, so what we do is we divide this into different parts of the electromagnetic spectrum, and this is the full spectrum here. So we go from gamma rays to X-rays, UV, ultraviolet, to IR. But in between UV and IR, there's visible light here. Visible light just occupies a small portion of the spectrum. The visible light is what we can see. UV is invisible, infrared is invisible. In fact, all of these are invisible except for the visible. And it's a tiny part of the spectrum, so we'll just expand it here so we can see the colors of the visible spectrum. The colors of the visible spectrum range from red up to violet. And so people usually remember this as Roy G. Biv. Red, orange, yellow, that's our Roy. G is green, Biv is blue, indigo, violet. So red, orange, yellow, green, blue, indigo, violet. Roy G. Biv. In terms of energy, we're going from high energy, high frequency, short wavelength, to low energy, low frequency, long wavelength. And so it turns out that red is going to be lower in energy than violet. Red is lower energy, longer wavelength, lower frequency. Violet's higher energy, shorter wavelength, higher frequency. And so we have to keep track of these things here. So this is the electromagnetic spectrum. Here we can see differences in wavelength. This is long wavelength, lower frequency. In terms of light, if this were light, longer wavelength, it's lower energy, lower frequency. Shorter wavelength is given by the symbol lambda. Wavelengths vary by orders, many orders of magnitude. So shorter lambda, shorter wavelength, means higher frequency, higher energy. So when we add up all the colors of the rainbow, we end up with white light. And so white light consists of all the colors of the rainbow. But we can split up white light into the component colors of the rainbow, that is, by passing the white light through a prism here, and then spread out the colors. So the sun emits white light. So if we take sunlight and pass it through a prism, we see all the colors of the rainbow. Basically, what's causing the sun to emit light? Well, there's a fusion reaction, and that fusion reaction is releasing a lot of energy. And what happens with that energy is it excites the hydrogen, helium in the sun, and causes them to collide very violently and produce electrons. And electrons get broken off the atoms, and those electrons get excited, but they don't stay excited forever. Eventually, the electrons will cool down. When they cool down, they emit light, they emit white light. So there are other things that emit white light. Like an incandescent light bulb. These.
What's the difference between wavelength and frequency?
Wavelength and frequency, they're related. Wavelength is the peak-to-peak distance in the wave here. And so when we look at it, let's look at the ocean wave here. We just measure how many meters is that distance compared to this. Now, if you have, let's say these two waves are moving at the same speed. If you have the two waves moving at the same speed and the wave is crashing into you, when the wave is crashing into you, this one has a lower frequency. That is, the frequency is given in hertz. So what's going to happen is you're going to, as the wave passes you, you're going to rise up to the peak here, and then drop down, and then rise up again. And so one of these where you start in one position and you end up in the same position is called a cycle. And so here, this one will have a lower frequency, that is fewer cycles per second than this one. This one, you're going to have more cycles per second. That is if both waves are traveling at the same speed. Well, all light travels at the same speed. It's the speed of light. And so what this means is long wavelength always means low frequency. That is fewer cycles per second. Short wavelength always means higher frequency. That is more cycles per second. Maybe animation might be better if you see this. Show you. Here they're varying the energy of this particular wave. So lower energy, longer wavelength, lower frequency. They should all be moving at the same speed, but you can see that this one would oscillate like this, whereas higher energy is a higher frequency, so it's oscillating a lot faster. So you can take a look at light here. What we're looking at is how light and matter interact. initially. When we have a wave like this, as an electric field, let's call the top positive and the bottom negative. An oscillating electric field switches from positive to negative, like this. Matter, you have the nucleus. The nucleus is positively charged, but it's heavy compared to what? Compared to the electrons. The electrons are a lot lighter. And so the nucleus is going to be influenced by the field. The nucleus is positively charged, so positive and positive, then like charges will result. Positive and negative attract. But the nucleus is somewhat massive and has inertia, whereas electrons are very light. And so if I have an electron here, the electron can oscillate with the field quite easily. And so here, if I have an electron here, well, the field's positive, boom, up. But then the field goes negative, it repels. And so what happens is the electron will start to oscillate with the field, like this. So let's start off with radio waves, which are the lowest energy. Radio waves have, let's start off radio. Radio waves have low energy. They're long wavelength, which is lambda, and low frequency, which is mu. And so radio waves, you know what used to happen? Car antennas, I don't know, if you have a really old car had metal antennas like this. Sometimes the metal antenna would break off, and then sometimes you'd see people replace their metal antenna with a coat hanger, metal coat hanger. Have you ever seen that? So they just get a coat hanger and replace it. And otherwise they wouldn't get good radio reception. If they want good radio reception, radio waves travel at the speed of light, and you want to capture that signal from the radio station. And if you didn't have any metal, you know, for example, let's say you had a plastic coat hanger. Plastic coat hangers don't work very well. Do you know why? You want metal coat hangers. You want metal coat hangers because the electrons are very loosely held in metals. And so when the radio wave comes along, the loosely held electrons can oscillate with the field, and then that picks up the signal from the radio station. Whereas if you had a plastic coat hanger, the electrons are very tightly bound to the atoms and the bonds. And so the electrons in the plastic coat hanger don't oscillate. So you never see people with a plastic coat hanger. They're using metal coat hangers for this. But what radio waves do is they oscillate, or we call this excite, you know, when it starts to oscillate. They excite electrons in metals. But in like plastics, the insulators, they don't really excite any electrons. Not enough energy.
What about like old cell phones? Called out.
Yeah,
Is it not plastic or is it metal?
there's metals, but the antenna is very weird in cell phones because cell phones operate at a higher frequency than radio waves. And so you just don't have a regular antenna. The antenna has to be tuned for the frequency that they're operating the cell phone at, and it's going to be part of the wavelength of this. Normally when you have an antenna, you want to tune it. You know, and so you have different sizes of antennas and stuff.
The technology has just gotten better than what it was then.
Yeah, the Newer antennas, like that little antenna on the cars now, yeah, it's much better. Antenna technology's gotten a lot better. What's higher in energy than radio waves? And so let's take a look at the electromagnetic spectrum. Let's see. Electromagnetic spectrum, people actually memorize this. In Chem 1A, and in fact in Chem 4, you're supposed to have this memorized. So, we have the radio waves here. These long radio waves are like your brain waves. Forget about those. So, we go radio waves, AM, FM. FM is megahertz. Have you heard of megahertz on the dial? Or AM is kilohertz on the dial. So, it goes to million hertz, a million cycles per second. Then we go to microwaves. Microwaves are a little higher in energy, a little shorter in wavelength, and a little higher in frequency. So if you put a metal, do you know what happens? Have you ever tried to put metal into a microwave? Yeah. Accidentally, what happened? You got sparks. Have you seen that?
I put plastic in the microwave on accident.
Okay. Yeah, did it melt or what?
It burned.
It burned, yeah. And then it just got too hot and started to decompose.
There's some weird thing that happens with grapes. So have you seen that?
No, I haven't. Yeah, I think I heard about that, but I can't remember it.
It's something to do with that the grape is the exact length or like
Oh, yeah.
length of the actual wave, the actual microwave.
Yeah, the wavelength is around 5 to 6 centimeters. So grape, yeah, a grape would work too long. Let's see metal in microwave. I don't know. They should show metal in there. Okay, do you see all the sparks?
That's what happened when I put the plastic.
Oh,
Yeah.
okay.
It's funny.
Well,
Thinking back on it, it's funny.
microwaves overly excite, or when you overly excite, we call it ionize metals. Ionize is just knock the electrons off metals. And so radio waves are enough to excite them, like this, oscillate, but microwaves oscillate them too much that they break off. So that happens. So
would you still consider microwaves as having like low energy, long wavelength, and low frequency?
compared to X-rays and gamma rays, yeah.
So microwaves and radio waves are like kind of the same.
Yeah, around the same. Microwaves are a little higher. We go from radio waves to microwaves to infrared. Infrared, what this does is it has the potential for ionizing metals, but usually infrared will cause vibrations, cause bonds to vibrate. And so we looked at the vibrations of water molecules and other complex molecules. So infrared energy causes those molecules to vibrate. Causes bonds of molecules to vibrate. And then we have visible. Visible is broken up. Next to red is, next to infrared is red. And so we go from infrared to red, and then we go to yellow. No, sorry, I missed one. Red, orange, yellow. Do you know the others? Roy, that's Roy, G, green,
Indigo,
blue, indigo,
and then violet.
and violet. Um,
What about blue? Yeah.
This is what excites electrons in matter.
So
This is what causes the colors to occur.
when you say visible, you mean like that's under the umbrella of infrared?
no,
Oh, so it's a different thing?
yeah. Infrared's invisible, and then this is visible light that we can see
Oh,
with our eye.
visible. I see.
We can't see infrared.
So like with the, like the James Webb telescope, it's mostly infrared, right?
Mhm.
And so what do they do with the frequency there? Do they shift it into the visible spectrum?
No. What they do is they use a detector to map it out. And so, like, the more intense infrared, they'll put a color to it.
Okay, so but it's not actually,
No,
it's just a representation of it.
right, yeah, just a representation so that you could see what it would look like. And then, they just make an arbitrary color for different regions. So visible light excites electrons in matter and it causes colors to occur. Red is the lower energy visible light. Longer wavelength, higher, or not, longer wavelength, not higher, lower frequency. Violet is at the higher energy end of visible light. And it's going to have a shorter wavelength and a higher frequency. Okay, what's beyond violet? Ultraviolet. So next comes ultraviolet on the other side of violet. And ultraviolet is going to have even more energy than violet, an even shorter wavelength, and an even higher frequency. And ultraviolet can break bonds in molecules. So it excites the electrons in the bond that cause them to break. Overly excites them. And then higher energy than ultraviolet is X-ray. And then even higher in energy than X-ray is gamma ray. Gamma is given this symbol like this, or you can spell it out, G-A-M-M-A. And X-rays and gamma rays, these ionize matter. Not just metals, but all matter. And therefore, these last two are called ionizing radiation. Radio waves are, light waves, all they can ionize are metals, but gamma and X-rays can ionize lots of things. And so this is very damaging. And so this is going to be the highest energy light, which is going to have the shortest wavelength and the highest frequency. Well, so there are different ways to make light. The sun makes light, essentially exciting electrons. When you excite electrons, they don't stay excited forever, and they'll eventually relax back down to a lower energy state. But the first law of thermodynamics, did I talk about the first law of thermodynamics? Energy is neither created nor destroyed. Yeah. And so if the electrons are high energy and they drop down to lower energy, the energy's got to go somewhere, and that energy goes off as light. And so in the sun, you have very excited electrons, and these excited electrons don't stay excited forever. They drop down in energy and emit light. And they emit all kinds of light. They emit infrared, you can feel it. You can't see it. They emit visible light, you can see it. It's white light. You can see the colors of the rainbow if you pass it through a prism. And they emit ultraviolet. A lot of the ultraviolet is captured by the ozone layer, that is absorbed by the ozone layer. They can emit X-ray, gamma ray, perhaps, but maybe those don't get to Earth. So some of the ultraviolet does, so that's fine. I have to talk, but anyway, I guess we're just about out of time. And so the thing is, how do you make a light bulb? You can't capture the sun into a tube or bulb. And so how to make a light bulb is this. Do you see the metal here? This is called the filament. This is made out of tungsten. Why tungsten? Because tungsten has a very high melting point. And what you can do is pass electricity through this. If you pass electricity through this, it gets very hot. And the hotter it gets, the more excited the electrons become. And so as this gets hotter and hotter, it'll start to glow. First, it starts to glow red hot. So we'll have red hot, and then orange hot, yellow hot. Eventually, it'll glow white hot. When it glows white hot, it's emitting all the colors of the rainbow. And that's what a light bulb is. It's just a piece of metal glowing white hot because electrons are very excited. And they don't stay excited forever. They'll drop down. And they drop down to different energy levels, or they get excited at different energy levels. So here you may have some very excited electrons emitting violet. And here you'll have less excited electrons emitting red, but we have all the colors in between. So we got a white light. Does that make sense? So that's the light bulb. It's just heating up a piece of metal until it's glowing white hot. But most metals, when you start glowing them white hot, they'll start reacting with air and become oxidized quickly. And so this inside the bulb is filled with nitrogen with no oxygen. If there's oxygen in here, then it'll oxidize the tungsten. When tungsten becomes oxidized, it forms tungsten oxide, which is brittle and breaks and doesn't conduct electricity. And so we can't let any O2 inside here. So this has been sealed with nitrogen. We'll talk about light bulbs more next time, so we'll stop here. Were there any questions for the test?
I just had a question about the electrolytes.
Okay.
So, let's say you had like an acid like H2S, but it, as a gas, not aqueous, would that be non-electrolyte, like a non?
H2S gas? Yeah, that would be non.
So anytime there's like an acid that's a gas, it's automatically gonna be
None, because you need water to pull apart the ions. That's the reason. Uh-huh.
I noticed that some
so these two.
a combustion reaction,
Mm-hmm.
and they would be I would do the CO2 and water,
Mm-hmm.
and a lot of times in the answer sheet, like I would assume that the carbon dioxide would be gas, and then we would add it down to
That's a typo.
or aqueous or something.
Carbon dioxide aqueous?
Yeah.
Carbon.
But when it should, but I would expect it to be gas.
It would be gas.
And then the steam would be gas.
Yes.
And then we put the H2 on the
Okay, that's a typo then. Those are got to be typos.
and I saw it all over the place.
Yeah, well, that's there's probably a lot of
I
those.
just didn't know.
No, you're right. You know, it would be gas. CO2 would be a gas, and H2O, yeah, steam would be a gas. H2O gas. So you're right. That's wrong, actually.
Can you bring interest in episodes today? Which one?
Yeah. Okay. Yeah, I'm having in-person office hours today at 4:20.
I was also wondering if I could take, I wanted to do like all problems in chapter 10,
Mm-hmm.
this practice. Do you have the answer key with the
I don't have the ones for chapter 10, but you don't have to do all of chapter 10.
Oh, yeah, I just wanted to do it. Not all of them, but the ones that we
Okay, those mass to mass.
Yeah.
Do all those. I'll check it.
Okay.
Yeah.